All right, so let's continue. Now, just a few definitions. X5 and X6 are called artificial variables. That are not part of the original problem. Original LP problem. Okay, so that's the first observation. The second one is that so we just need them to find an initial basic feasible solution. Basic feasible solution in an easy way. Thirdly, m is a very big positive number. And fourthly, so we try to make all artificial variables equal to 0. We try to make all artificial variables equal to 0 using the objective function, using the new objective function. So essentially, one way to think about this is I'm adding variables x5 and x6 both to my constraints and to my objective function. So I'm changing the problem in some sense. But at the same time, I want to make sure that my new problem is related to my previous problem. Okay, so essentially, by finding a solution in which x5 and x6 are both equal to 0, then that already gives me a solution for the original problem. Okay. So from this point on, just apply the simplex method as is. Okay, but we're going to use the simplex method on the new problem. Okay, new problem means the one with the additional variables. So I'm going to set up the tableau. Now, what does row 0 look like? Well, I'll start with z, which is a coefficient of 1. Then I'll just negate every coefficient, right, in the objective function. So I'm going to have 4, 1, 0, 0. For x5, I have m, and m as well. The right-hand side is 0. Okay? And then I'm going to just sort of copy my constraints. So row 1 will be given by 3, 1, 0. There's no x4, so 0, 1, 0, and the right-hand side value is 3. Then row 2 will be given by 0, 4, 3, minus 1. Then I have 0, 0, 1, and the right-hand side value is 6. And finally, row 3 will be given by 0, 1, 2, 0, 1, 0, 0. And the right-hand side value is 4. So now, unlike the original problem, we do have a starting solution here, right? How so? Well, if I look at the columns underneath x5, x6, and x7, they give me exactly columns of the identity matrix, okay? So the basic variable for row 1 will be equal to x5. For row 2 is going to be equal to x6. And for row 3 is going to be x4. Okay? Now, this is also important. Please pay attention. Before I start the simplex method, there's one thing that I need to take care of in this solution. So remember, in the simplex tableau, whenever I have my basic variables, its row 0 coefficients are all equal to 0, basically, right? So every time I have a basic variable in the simplex tableau, and when I look at its row 0 coefficient, it's always equal to 0. Okay? However, in this case, despite the fact that x5 and x6 are basic variables, their row 0 coefficients are not equal to 0. Okay? Now, this problem never showed up before because we started with select variables, and the select variables always had 0 in the objective function. Okay? So we never had this issue before. But in this case, since we also have non-zero coefficients for x5 and x6 in the objective function, before I can start the simplex method, I need to make sure that both of these entries are equal to zeros. Okay? Another way to say this is the following. If you also include z as your basic variable, Then I have the first column of the identity matrix, 4 by 4 identity matrix now, 1, 0, 0, 0. For the second column, I should have a 0 here, basically, right? 0, 1, 0, 0. So I need to make sure that this entry becomes 0 first, okay? And similarly, for example, here I should have 0, 0, 1, 0. And this part is fine, 0, 0, 0, 1. So the problem is that I need to make sure that both of these entries are equal to 0 before I can start. Does everybody see that? Okay. And so, essentially, before I start, I need to make sure that I make these entries 0. And how would I do that? Well, I can take row 1, multiply it by minus m, and add it to row 0. Okay? And then I'm going to take row 2, multiply it by minus m, and add it to row 0. So basically, I'm going to take this row and multiply it by minus m, and add it to row 0. And I'll just do the same thing over here to make sure that I'll take care of these entries. Okay? To make sure that those entries will be equal to 0. Okay? So once again, I mean, in the simplex method, the row 0 coefficients of all basic variables should be equal to 0. Okay? However, in this case, that's not the case. So first, we need to put it in the correct form so that we can start. Is that clear? Well, if this is not clear, please go back to your notes and make sure that whenever you have a basic variable, all the row 0 coefficients are 0. Okay? And in this case, this is not true. So first of all, I need to make sure that the row 0 entries of x5 and x6 become 0. And only after that, my tableau is in the right form and I can start. Okay? If I don't do that, then all my steps will be wrong, basically. Okay? So if I don't do that, so if I look at the current solution, basically it tells me that this is optimal, right? Since this is a maximization problem, there's no negative coefficient. If I don't do the step, then I will incorrectly say that this is the optimal solution. But this is not the optimal solution, as you will see. Okay? So as a result, in the first step, you just need to do this. And if you do this, you get the following. So just multiply the first row by minus m, second row by minus m, and add it to row 0. So this part does not change. I still have 1 here. What's the new coefficient of x1? So I'm going to have 4 minus 7m, basically, right? Okay, there's no more 4 here. What about this part? So I'm going to have 1 minus 4m. Okay. What about this part? I'm going to have plus m. What about x4? Well, that does not change. For x5, I'm going to have minus m plus m, so I get 0. So this part disappears. And for this one, I have minus m plus m. Again, I get 0. And what about the right-hand side value? So right-hand side value, minus 3m minus 6m, so it's going to be minus 9m. Well, minus 9m is a pretty bad value for the objective function, right? Okay, remember m is a very large number. This is a maximization problem. So indeed, if you just plug in these values, so x4 equals 4, x5 equals 3, and x6 equals 6 in the objective function, you indeed get minus 9m, right? So that's the correct objective function value. Does everybody see that? Okay. So now my tableau is in the correct form. So once again, please make sure that you do this step before you start. Okay. So now I should ask myself, is this an optimal solution? Well, to answer this question, you should always keep in mind that m is a very large number. Okay, so m is a very large number. So for example, if I look at the row 0 coefficient of x1, that's given by 4 minus 7m. Okay, but think of m as a very large number. So as a result, 4 minus 7m is actually a negative number. Okay, so think of m as like million or something like that. Okay, similarly, for example, the coefficient of x2 is negative as well because 1 minus 4m is negative. Okay, so again, the easiest way to think about this is m dominates every other number, basically. Okay, so if m has a negative coefficient, then that entry is negative. Okay, and if m has a positive coefficient, then that entry is positive, regardless of what the other number is. Okay, in general. So as a result, is this an optimal solution? Well, the answer is no. I should be looking for a negative coefficient in row 0, and there are 2 of them, basically, right? So both of these 2 variables have negative coefficients, and this is a larger negative coefficient. Right? Because 7m is larger than 4m. So I'm going to enter x1. And then I'll just perform a minimum ratio test. What's the ratio for row 1? So it's given by 1. What about row 2? It's 1.5. For row 3, it's 4. So as a result, x5 actually has the smallest ratio. x5 will leave. And I'm going to pivot on this entry. Okay? So from this point, that's just the regular simplex method, basically. Okay, so there's nothing new after this. So this is what the next tableau looks like. So first of all, I'm going to pivot on this entry. And if I do that, I have 0, 1, 1 over 3. Divide everything by 3, basically. 0, 0, 1 over 3, 0. And the right-hand side value is 1. Then I want to zero out this entry and this entry. And similarly, I want to zero out this entry as well. And the new row of 2 looks like the following. 0, 0, 5 over 3. Minus 1, 0. Minus 4 over 3. 1 and 2. So essentially, I'm just multiplying this by minus 4 and adding to row 2. And this is what you have. And the new row 3 looks like the following. Again, I'll take this row, multiply it by minus 1, and add it to row 3. And if you do that, you have 0, 5 over 3 again. 0, 1, minus 1 over 3, 0, and 3. So this is the new row 3. Then I'm going to take this row, multiply it by minus 4 plus 7m, and add it to row 0, basically, right? So I'm going to take this row, multiply it by minus 4 plus 7m, and add it to this row. Okay? And if you do that, you have 1. The new coefficient becomes 0. So here you have minus 1 over 3, minus 5 over 3m. This one? So I'm multiplying this by minus 4 and adding it to row 2. So minus 4 over 3 plus 3 is equal to 5 over 3. Right? I'm taking this row, multiplied by minus 4, and adding it to row 2. So minus 4 plus 4 becomes 0. Minus 4 over 3 plus 3 becomes 5 over 3. Right? Okay? And so on and so forth. Is that clear? Okay. So, I mean, this is a bit tricky. So here you should be careful. You're going to multiply this new row by 7m minus 4 and adding it to row 0 again. Okay? And if you do that, these are the new coefficients. You have 0. You have minus 4 over 3 plus 7 over 3m. This is still 0. And the right-hand side value is minus 4 minus 2m. Okay? Mm-hmm. Well, this is just a regular simplex step, right? So x1 enters, x5 leaves. So I'm just pivoting on this entry. I'm not doing anything special. Okay? All right, so, I mean, of course, it gets a bit more complicated because there are m's, basically. But other than that, it's just the usual simplex method. So x1 enters, x5 leaves, and I'm pivoting on this entry. Okay? So what are the basic variables? What's the basic variable for row 1 now? So it's going to be x1. What about row 2? It's still x6. And row 3 is still x4, right? Now, this is my new basic feasible solution for the new problem again. Okay, I'm still working with the new problem. The objective function was minus 9m. Now the new objective function is minus 4 minus 2m, which is larger than minus 9m, right? So the objective function value actually improved. Okay? It was like, minus 9 million. Now it's about minus 2 million. Okay, so I'm actually doing better right now. So next, the question is this an optimal solution? Well, once again, I should look for a negative coefficient. Obviously, this is a negative coefficient. What about this one? Well, since m is very large, again, m dominates the negative term, so this is actually positive. Okay, so since m is a very large number, this is actually a positive coefficient. So there's only one choice, which means that I need to enter x2. Now, what's the leaving variable? Well, I'll just apply the minimum ratio test. Ratio for row 1 is 1 divided by 1 over 3, which is equal to 3. So here I have 2 divided by 5 over 3, which is 6 over 5, which is 1.2. So here I have 3 divided by 5 over 3, which is 9.5, which is equal to 1.8. Okay? So this one is the smallest one, basically, right? Okay? So x2 enters and x6 leaves. So what am I going to pivot on? Well, I'll just look at the entering variable, the leaving variable, and that's the intersection. So again, I'll just do a usual simplex step, okay? So I'll just pivot on that entry. And so this is what we have. So as a first step, I'll just, again, turn this into 1, entry into 1, and everything else in this column will be zeros, basically, right? So I'm going to multiply row 2 by 3 over 5. And if you do that, you have the following: 0, 0, 1, minus 3 over 5, 0, minus 4 over 5, 3 over 5. And the right-hand side value is 6 over 5. So this is the new row 2. Just multiply the old row 2 by 3 over 5, basically. Okay. Then I'm going to take new row 2, multiply it by minus 5 over 3, and add it to this row. And if you do that, you have 0, 0, 0, 1, 1, 1, minus 1. And the right-hand side value is 1. So I just zeroed out this entry right here. Then I'll just do the same thing for this one. I'm going to take the new row 2, multiply it by minus 1 over 3, and add it to row 1. And if you do that, you have 0, 1, 0, 1 over 5, 0, 3 over 5, minus 1 over 5, and 3 over 5. So this is my new row 1. Then I need to make sure that this entry is 0. Okay? And to do that, I'm going to take the new row 2, multiply it by 1 over 3 plus 5 over 3m, and add it to this row. Okay? I mean, the algebra is complicated, but it's a simple idea. So you get 1, 0, 0, minus 1 over 5, 0, minus 8 over 5 plus m, 1 over 5 plus m, and the right-hand side value is minus 18 over 5. All right, so what are the basic variables for this solution? So I have z here. What's the basic variable for row 1? x1. Basic variable for row 2? x2. And for row 3, we have x4. Now let's just sort of look at this basic feasible solution. So what are my basic variables in this case? x1, x2, and x4. And x1, x2, and x4, they all come from the original problem, basically, right? So essentially, at this step, I found the basic feasible solution for the original problem. Okay? So if I pick x1, x2, and x4 as my basic variables, then I get the corresponding basic feasible solution for the original problem. Okay? x5 and x6 are no longer in the picture because they're non-basic. And since they're non-basic, their values are equal to 0. Okay? So which means that, you know, x5 and x6 actually did their jobs, so they can leave the picture now. Okay, so let me write it down. Since x5 and x6 are both non-basic, this BFS is also a basic feasible solution for the original problem. Okay? And note that the objective function value also increased again. So we were like, minus 2 million. So now we're only minus 18 over 5, which is much better. Okay? So there are no artificial variables in the basis. So as a result, at this stage, and I know that if you look at the coefficients of x5 and x6 in row 0, their coefficients are positive and very large, basically, right? Because of m. So which means that if I try to increase x5 or x6, that will never help me, basically, right? That will always make my objective function value worse. So at this stage, you can now get rid of x5 and x6 altogether. So you can actually delete the columns corresponding to x5 and x6 because you know that they will never re-enter the basis again. Okay? And part of the reason is that that's the reason why we picked coefficients, big coefficients for x5 and x6 in the objective function. Okay? So increasing them will never help us. Okay? So as a result, I can simply get rid of x5 and x6, and I can continue with the original variables now. Okay, I have only x1 through x4. So is this an optimal solution for the original problem now? So now I'm actually looking at the optimal original problem. Well, there's still negative coefficient. So x3 enters. And what's the leaving variable? Well, just apply the minimum ratio test. Ratio for row 1 is equal to 3. Ratio for row 2, there's no ratio. And ratio for row 3 is equal to 1 again. Okay, so what's the leaving variable then? Well, 3, no ratio, 1, so obviously x4 has the smallest ratio, so x4 leaves. Okay, so I'm going to do one more pivot. And which entry I'm going to pivot on? So x3 enters, x4 leaves. I'm going to pivot on this entry, basically. So let's do that. So now I'm going to only keep the original variables. I don't need the artificial variables anymore. So row 3 is fine already, so I don't need to do anything. I have 0, 0, 0, 1, 1. The right-hand side value is 1. Then I will just zero out everything else in the column corresponding to x3. So multiply this row by 3 over 5 and add it to row 2. And if you do that, you have 0, 0, 1, 0, 3 over 5, and 9 over 5. And then take this row and multiply it by minus 1 over 5 and add it to row 1. And if you do that, you have 0, 1, 0, 0, minus 1 over 5, and the right-hand side value is 2 over 5. And then finally, take this row, multiply it by 1 over 5, and add it to row 0. And if you do that, you have 1, 0, 0, 0 again, 1 over 5, and minus 17 over 5. So once again, this is a basic feasible solution of the original problem. Okay, so we no longer need the artificial variables anymore. And if you look at row 0 coefficients, there's no negative coefficients underneath the non-basic variables. So indeed, this is the optimal solution, right? Okay. So once again, let me just quickly go over what we did. So I introduced these artificial variables, x5 and x6, to form the columns of the identity matrix. Okay? So x5 and x6 are not part of the original problem, but they're artificial variables that I'm using just to construct an initial basic feasible solution. But at the same time, I want to get rid of them in the optimal solution. Okay? And for that purpose, I'm actually introducing these coefficients into the objective function. Okay? So basically, these coefficients make sure that increasing x5 and x6 never help you in terms of the objective function value. Okay? So this is the first tableau that we start with. But the problem is that I'm going to use x5 and x6 as the basic variables, but originally the row 0 coefficients are not 0. So first I need to make sure that they're equal to 0. So this is the first, think of this as pre-simplex method step. Just before applying simplex method, you need to perform this. And then after this point on, it's just a regular simplex. Okay? With the, of course, understanding that m is a big number. M is a big, large number, so m dominates everything else. So which means that 1 minus 4m is actually negative, 4 minus 7m is negative, and so on and so forth. Okay? And then we just enter the most negative coefficients, and we do the usual minimum ratio test. This is next solution. That's the third solution. And at this stage, all of the artificial variables are out of the basis now. Okay? There are no longer any basic variables which are artificial. So we can get rid of them altogether. So we're only left with the original decision variables, or decision variables of the original problem. And then we continue and we find the optimal solution. So one thing to keep in mind is that, for example, this solution is a BFS for the new problem. And if I get rid of x5 and x6, it's also a BFS for the original problem as well. Okay? So in a sense, I mean, x5 and x6 at this stage completed their jobs, and they can leave the picture now. Okay? So they actually helped me find a feasible solution for the original problem. And then from this point on, I'm only dealing with the original problems, original decision variables, basically. Okay? Yes?
Is there any possibility of, like, x5 for x5 and x6, the m value may be negative, has a negative coefficient?
You mean right here?
Yes.
Well, okay, let's think about it again. So if I look at the objective function, okay, making x5 or x6 positive always decreases my objective function, right? Okay? So as a result, this is the reason why I'm actually picking these values for my artificial variables, okay, as the cost coefficients. So as a result, increasing x5 and x6 never helps me, basically, okay? And if you think about this a little bit, note that x5 is leaving the basis in the first step, x6 is leaving the basis in the second step. So essentially, my problem is trying to get rid of these variables as fast as it can, in some sense, okay? So introducing those variables back to the basis never helps me, okay? It always makes my objective function value worse than what it is right now.
Is there any possibility when we multiply it with numbers, like we do it, is there a possibility of making it?
So let me put it this way then. So when an artificial variable leaves the basis, it will never come back. Okay? If it does come back, then you're making a mistake, basically. Okay, that's a good check, basically. Okay, so for example, x5 leaves the basis in the first solution, then x5 will never come back to the basis again. Okay, that's the property of the big M method. And x6 leaves the basis in the second step, and x6 will never come back again. So that's the reason why I can get rid of these two now. Okay, I don't need to carry out my operations for these two variables. Okay, other questions? All right. So let me give you another example. But is the main idea clear at least? I mean, so it's a nice idea. It's a simple idea, but it actually works. This is example 2. So suppose that now we have a minimization problem. So minus x1, minus 3x2, plus x3, subject to x1 plus x2 plus 2x3 is equal to 4, minus x1 plus x3 minus x4 is equal to 4, and then x3 minus x5 is equal to 3. And then x1, x2, x3, x4, and x5 are all non-negative. So now this is a minimization problem. Again, the problem is already in standard form, so I don't need to do anything else. But once again, this is a problem, just like the previous one. There's no readily available initial basic feasible solution to start with. Okay, so it's just the same example. So the first step is to sort of decide, which constraints actually need artificial variables. Okay, so that's the first step that we need to think about. Let's start with row 1, or the first constraint. Well, if I look at x2, I already have the first column of the identity matrix here, right? So I have 1, 0, 0. So basically, for row 1, I can use x2 as the starting variable. Is that clear? Okay. What about row 2? Well, I'm looking for the second column of the identity matrix. Well, I have 0, minus 1, 0, but that's not quite what I want. Okay. So I need a second coefficient, which is 0, 1, 0. So as a result, I'm going to introduce a variable, which I'm going to call x6, for row 2. So now I have 1, 0, 0 underneath x2, 0, 1, 0 underneath x6. Okay. What about the third constraint? Well, again, the same situation. We have 0, 0, minus 1, but that doesn't quite work. Okay. I need the third column of the identity matrix, so I'm going to need plus x7 for the third constraint. Okay. So x6 and x7 will also be non-negative. Now, this is important again. So how am I going to modify my objective function? Well, so this was a maximization problem, and I'm penalizing my decision variable. So that's why I multiply by minus m, right? That's a minimization problem. Okay. So how would I penalize them? So instead of minus m, I'm going to have plus m right now. Okay, for a minimization problem. So the new coefficients will be m times x6 plus m times x7. So once again, if I increase x6 or x7, then my objective function value will increase significantly. And that's not what I want because it's a minimization problem. Okay? Please be careful here, because if you write down minus m here, then you're going to be in trouble. Okay? If you write minus m, then you want to increase the values of x6 and x7. This is a minimization problem. Okay? So then for a maximization problem, the coefficient is minus m. For a minimization, the coefficient is plus m. And intuitively, that makes sense, right? So I should pick them in such a way that I don't want to increase the values of x6 and x7, basically. Okay? So let's set up the simplex tableau again. So let me start with row 0. I have 1. Then what are the coefficients for row 0? Somebody help me. 1, 3, minus 1, 0, 0, minus m, right hand side is 0, right? Okay. All right, so let me start with row 1. So 1, 1, 2. I'll have 0, 0, 0, 0. Right hand side is 4. Then row 2 will look like 0, minus 1, 0, 1, minus 1, 0, 1, 0, and 4. And then row 3 looks like 0, 0, 0, 1, 0, minus 1, 0, 1, and 3. So let's figure out the basic variables. What's the basic variable for row 1? I'm going to use x2, right? What's the basic variable for row 2? So I'm going to use x6, which is an artificial variable, and then x7, right? So once again, this is where you should be careful. So my basic variables are x2, x6, and x7. So the row 0 coefficients all should be equal to 0, okay, before I can start, okay? But in this case, the row 0 coefficient of x2 is 3, so I need to make it 0. The row 0 coefficient of x6 is equal to minus m, I need to make it 0. And the row 0 coefficient of x7 is equal to minus m, I need to make it 0, basically, right? Okay, before I can start. So how am I going to achieve that? Well, I'm going to take the first row, multiply it by minus 3, and add it to row 0. So that will make this entry equal to 0. Is that clear? So then I'm going to take row 2 multiplied by m and add it to row 0. So this will become 0. And I'll just do the same thing for this one as well. Okay? So as a result, I'm going to take the first row multiplied by minus 3, take the second row multiplied by m, take the third row multiplied by m, and add it to row 0. Okay? And by doing that, the row 0 coefficients of all basic variables will be equal to 0. Okay? And if you do that, this is what you have. So this part will disappear, basically. And instead, you're going to have minus 2 minus m. So basically, think about it this way. So minus 3 minus m. So I get minus 3 minus m plus 1 is minus 2 minus m, basically, right? Okay? So this part becomes 0. Here you have 2m minus 7. Here you have minus m, 0, 0. And the objective function is minus 12 plus 7m. Turkish. So this is my initial basic feasible solution for the new problem again, okay, for the modified problem, for the problem that includes the artificial variables. The objective function value is pretty bad again, so it's minus 12 plus 7m, so think of m as like million. So right now I have like 7 million as the objective function value. This is a minimization problem, so what should I be looking for? So I should be looking for a positive coefficient in row 0, right? So is there a positive coefficient in row 0? Well, obviously this is negative, okay? So this is already basic. Well, since m is a large number, 2m minus 7 is actually a positive number, right? So as a result, I should actually increase x3. Then I should figure out the leaving variable. So I have 2 as the ratio in row 1. I have 4 as the ratio and 3 as the ratio. The smallest one is this one. So x2 leaves. So as a result, I'm going to pivot on this entry. So what does second tableau look like? Well, so I have z, x1, x2, x3, x4, x5, x6, x7, and the right-hand side. So just usual simplex iteration. So make the center equal to 1, multiply everything by 2. So you have 0, 1 over 2, 1 over 2, 1, and everything else is zeros. Right-hand side becomes 2. And then I'm going to multiply the new row 1 by minus 1 and add it to row 0. Add it to row 2, sorry. So this entry becomes 0. So if you do that, you have 0 minus 3 over 2, minus 1 over 2, 0 minus 1, 0, 1, 0. The right-hand side is 2. And then finally, I have 0, 0, sorry, 0 minus 1 over 2, minus 1 over 2, 0, 0 minus 1, 0, 1, 1. So essentially, I just zeroed out these terms. Okay, so now I'm going to zero out this term as well. I'm going to take the new row 1 and multiply by 7 minus 2m and add it to row 0. And if you do that, you have 1, 3 over 2 minus 2m, minus m plus 3 over 2. Then you have 0, minus m, 0, 0, and the right-hand side value is 2 plus 3m. So this is the next basic feasible solution, again, of the new problem, of the modified problem, okay? I still have artificial variables. Let's figure out the corresponding basic variables. So what's the basic variable for row 1? So it's x3, which replaced x2. For row 2, it's still x6. And for row 3, it's still x7, right? So this is a minimization problem, okay? Is this solution optimal? This is a minimization problem, so what am I looking for? Positive coefficient in row 0. So is this positive? No, m is large, so this is negative. What about this one? Again, this is negative as well. This one is negative, this one is negative. So this is an optimal solution, basically, right? Okay? So this solution is optimal for the new problem. So what's the new problem? The new problem is the one that I obtained after adding x6 and x7 into my problem, okay? So my question is the following. Now I was trying to solve the original LP problem, but I found the optimal solution of the new LP problem, the modified LP problem, and this is my solution. Now one thing you should be careful is the following. x6 and x7 are both basic still in the solution, right? And they have positive values, okay? And since x6 and x7 are not equal to 0, I cannot get rid of x6 and x7, basically, right? Because if I do, then the equations will no longer be satisfied, okay? Unlike the previous example, okay? So now the question is the following. So what does this imply? So what kind of an information does this give me about the original problem? So let's think about this way, basically. Remember, so we were trying to drive x6 and x7 equal to 0, right? We were trying to sort of make them smaller and smaller if possible. But the best we can do is I can decrease x6 up to 2 and x7 up to 1, okay? So I can never make x6 and x7 equal to 0, basically. Now what does that mean about the original problem? Now think of it this way. Suppose that for now there's no x6 and x7, okay, in the system, okay? And suppose that there's a solution to this system, right? Okay? Without x6 and x7, okay? Now if there is a solution to the system, then I can turn it into a solution for the larger system by simply defining x6 and x7 equal to 0, right? Okay? And in that case, my objective function value will not include any value of m. It will only depend on x1, x2, and x3, basically. Okay? So which means that if there is such a solution, then that solution will not include x6 and x7, and the objective function value will not depend on big M. Okay? And that solution will be actually better than this one. Okay? So now let's reverse the argument. So if there were such a solution without x6 and x7, then I would be able to find a better objective function value. Well, I couldn't find a better objective function value. What does that imply about the original problem? Well, actually, without x6 and x7, there is no solution to this system. That's essentially what it means. Okay? In other words, the original problem without x6 and x7 is infeasible. Okay? So which means that it has no feasible solutions. As a result of which, the best we can do is we can only get x6 and x7 down to 2 and 1, but we can never make them 0. Okay? And since we can never make them 0, that implies that the original problem cannot have a feasible solution. Does that make sense? So let me write that down. If the original LP problem had a feasible solution, then we could find a feasible solution. For the original LP problem, by defining x6 equals 0 and x7 equals 0. However, we can never make x6 and x7 equal to 0 in this example. So therefore, this implies that the original LP problem is unbounded. The original LP problem is infeasible, So this is actually pretty cool, if you think about this a little bit, because the big M method not only sort of finds a solution, but it can also tell you if the problem does not have any feasible solutions. Okay, so if you end up with such a situation, then you just say that the original LP problem cannot have a feasible solution. And of course, if there's no feasible solution, then there's no optimal solution, basically, right? Okay? So of course, I mean, this was a problem that never showed up in the earlier examples, because in the earlier examples, the starting solution was already feasible using the static variables. So the problem was always guaranteed to be feasible. But in general, there are LP problems that are not feasible, and this is one way of finding out about the fact that there's no feasible solutions, okay? So the big M method can also tell you if the problem does not have any feasible solutions. Is this argument clear? So this is really important. I just want to make sure that everybody understands this. Yes?
But we can't make a negative variable enter and just make x6 and x7 live. So the objective function value will be larger, so we don't want that, but still maybe it will be feasible.
Okay, so for example, if I want to increase x2, right,
Yes.
then there's only one leaving variable, which is x3. Okay, so they will still be in the basis. Right, there's no minimum ratio here, right? Similarly, if I want to increase x1, again, there's no minimum ratio here. So these variables will always stay in the basis. Okay, so there's no way I can get rid of x6 and x7, so they will always be there. Okay, so as a result, unfortunately, it sounds like a nice idea, but that doesn't work. Okay? I mean, another way to think about this is basically, despite the fact that you're penalizing x6 and x7 in the objective function, the problem can still not make x6 and x7 equal to 0. Okay? So you still have to pay that penalty. Okay? Pay that cost. Okay? Well, if you still have to pay that cost, and if that's the best you can, then the original problem cannot have a feasible solution. That's the argument, basically. Okay? Other questions? All right, so let's stop here. We'll continue on Thursday.